All right, I'm Logan Blackwell, and this is my Scholar Day project, applying calculus to an oil spill. This is mostly a related rates problem, so I figured it was wise to give a quick introduction to related rates. Um, as the name would imply, related rates have to do with finding the rate at which some unknown quantity changes by relating it to quantities whose rates of change are known. And rates of change are just derivatives, so calculus. This makes it possible to find rates of change that might be really difficult to find otherwise. Some early examples that typically get shown to calculus students are like the legs of the side of a ladder makes as it slides down some vertical surface, or the length of a shadow over the course of a day. So the problem I'm actually going to look at is an explosion on an oil rig located in Gulf waters causes an elliptical oil slick to spread on the surface from the rig. The slick is a constant 9 inches thick. After several days, when that major axis of the slick is 2 miles long and the minor axis is 3/4 of a mile wide, it is determined that its length is increasing at the rate of 30 feet per hour and its width is increasing at the rate of 10 feet per hour. At what rate in cubic feet per hour is oil flowing from the side of the rig at that time? Our book gives a really basic strategy for approaching related rates problems, which is to draw a picture and name the variables and constants, define the variables, what they actually are, identify what you've been asked to find, write an equation that relates variables, differentiate with respect to time, and then evaluate the whole thing. So that's pretty much what I did. I made these quick little pictures demonstrating the area and volume of an ellipse and an elliptical cylinder. Something you've got to notice with this problem is that it gives the lengths of the major and minor axes as the whole diameter of the ellipse. But that's not what we have in the actual formulas for the surface area and volume of an ellipse. It only asks for the radius, so we have to divide everything in half. Additionally, we have to convert everything into feet because it's asking for cubic feet per hour and it gives us mixed units. And since it's asking for the flow rate, we're looking for the rate of change of volume. So we have the equations for volume and area here. Volume equals height times pi AB, and area equals pi times AB, which gives us volume equals height times A. And from there, we can differentiate with the product rule. So dV over dt equals area times dH over dt plus h times dA over dt. dH over dt is equal to 0 feet per hour, so we can get rid of that term entirely because multiplying by 0 gives 0. And then we have to find the derivative of the area formula, which is going to be, we can pull pi out and then apply the product rule again, which is going to give us A times dB over dt plus B times dA over dt. And that's all multiplied by height. And that is our formula for the rate of change of this ellipse's volume. And from there, we can just evaluate, plug everything in, which rounding to the nearest cubic foot gives 132,183 cubic feet per hour. Now, obviously, a real oil spill wouldn't be perfectly elliptical, nor would it have a constant depth, but treating it as an elliptical cylinder makes it a lot easier to estimate its rate of expansion, which is crucial for estimating the severity of the oil spill and containing it and cleaning it up and everything. Related rates are one of the clearest and most wide-reaching applications of calculus. They make constant appearances in science and engineering, and I intend to go into environmental science. And when I was doing research for this project, I found out that there's actually an entire course at one school in, I think, Indiana, that's just mathematics applied to environmental science, and a lot of it was related rates. But they aren't only used in science and engineering. They can apply to be applied to like DIY projects and cooking. And I'm sure there are other examples, but those were the ones that came to mind immediately. And those are my citations. That's pretty much my project.
Awesome.